Thank you. All right, so today we're going to continue with modeling of forces. We're going to do spring forces. Before I do so, I just want to reiterate on one comment we made a few times about apparent forces, these things that we heard forever until this point. I think I wrote down something from last example. I'm not sure this is exactly what we got, but there was a reaction force that ended up being 2m r dot omega, and again there may be something else here or some sign is different. I don't remember exactly, but this is a specific case where, what would you call this? At least with the old dynamics that we used to know, I was used to call something showing a 2 and a velocity and an angular velocity the Coriolis Force, right? One of those apparent forces. Well, guess what? In this specific case, this is an actual force. This is the is two objects that are touching each other, the tube or the arm, whatever we call this, and the particle of mass m, and this is the reaction that the arm is exerting on the particle m. So there's no reason to call this an apparent force. This is an actual force in this case. It ends up being this way. It's not always the case, but my point is that all those apparent forces, they're apparent. They don't exist. They're not real stuff. They don't come from contact of objects. They don't come from attraction from gravity. They don't come from a spring. They don't come from anything. They just are a product of a mass times all those terms in your inertial acceleration that come out by the fact that you have used probably coordinate systems attached to non-inertial reference frames to express A in G, but they don't exist. So I think my piece of advice is get away from that thinking that forces you to guess too many things and just do the kinematics first, and whatever comes out of that, it's your acceleration in the inertial reference frame. It may be super long because you use multiple coordinate systems along the way. That's fine. That's the way it is. M, A, G will be equal to your real forces, and that's the end of the story. I know it's hard to change thinking, but it does make it easier, I think. It really does, and it makes more sense because those forces don't exist. Okay, so spring forces. Linear springs, that's what we're going to see today. And we are going to do the same that we have done for friction forces. We're going to express vectors. Forces are vectors. We're going to do it that way and only that way. Now, there's nothing really linear in this world, of course. There's no such a thing as a linear spring, but again, it's a good approximation of what we observe in certain ranges. If you take an object that can deform and can react to a deformation, within certain limits, it may behave linearly. Again, these are models that allow us to apply the principles that we study. They don't mean to be exactly reality. Okay, so we start from the usual. I'm giving you a reference frame A, origin fixed in A. And in this reference frame and its coordinate system, I have a point, a particle of mass m, and another point q in 3D Euclidean space. And these two are connected by a linear spring, k. K is the constant for the spring. So we have, these are the ingredients, particle of mass m. Of course, there must be a mass, otherwise there's no kinetics. And then we have a generic point q, which I'm going to call the attachment point. And I'm going to say that the spring is linear. I'm going to say a little more about that in a second. Acting along QP. So the force that it can exert is along that direction. So linear is what you've seen so far. It basically means that the norm of the force exerted by the spring is proportional through that constant k that we attach to the spring to the deformation of the spring. So this is all norms, all scalars. I'm not writing vectors yet. Where delta L can be caused by a compression or elongation of the spring. Nothing new. That's usually what you have seen. You've always seen something like this, right? Which is not what we do here, because we do vectors. But that's what linear means. And again, it's an approximation. You may see other models out there that have nonlinear springs, that have quadratic terms in terms of the deformation, et cetera, et cetera. They exist. They are more refined models that they can represent physical systems. But we're fine with this. OK. Let's define a few things before we express what is the vector. So I want to find an expression. I want to define. Since this is a model, I make it up. I decide that f of s is going to be something I like, something that makes sense to me to represent that behavior, which is a linear spring. I need to define. OK, so of course, these points have a position, very well-defined position in the coordinate system attached to reference frame A. So this is RQ. Okay. Let's define that US, little us, be the unit vector from basically from Q to P. So U of S is defined as, how would you define U of S? With the information I've given you. It's the unit vector that goes from the attachment point to the particle of mass m. So keep moving this Q up and down here, I'm sorry. It's this unit vector here. How do you express that? Again, this is a three-dimensional case. Particle is in 3D, the Q is in 3D, this spring can move around in 3D. We're doing everything with three-dimensional vectors. Yep. Right? Rp minus Rq over its magnitude. That's a unit vector, right? Good. Then I'm going to say, that's one piece of the force that I'm going to put together. I'm going to say that the spring, what do we call this? Uncompressed or unstretched length of the spring is a given length, we call it L0, and then the actual length of the spring, so at any time that can change, of course, we call it L. What is L?
Instantaneous length of the spring?
It's the actual length. Just look at that and tell me what that is.
It's the magnitude of RP minus RQ.
Yep. Rp minus Rq. Everything we do in this class is geometry, it's vectors. You can always come down to expressing vectors. That's all we do. Accelerations, forces, they're all vectors. And in case we need scalars, we can define them from the appropriate vectors. That's the length. at any time, whatever those points are doing, I don't care, that's the distance between those 2 points, right? Okay, so what else do I need? I have the constant k, I have the direction from the point of attachment point to P, I have the length of the spring, the actual one, the unstretched one, so I can define this f of s. Okay. Remember, these are models. I define these things. So I'm going to say that the force f of s, this is of course a force that in this case goes on the mass of a particle mass m, that's the only mass I see there, is going to be expressed as minus k L minus L0 US. That's US. That is the one and only linear spring expression that you really want to use. And it's not simply taking an x, as we've done for years, and stick it in here, and just a constant here, and start thinking about if I compress this, if I stretch this, what happens, which way is the force. You don't need to do that craziness, because this is really including all the cases. You don't need to think about any sub-cases. You're more than welcome to start thinking about a case where Q is fixed in reference frame A, and you start pulling or compressing the spring and see if this makes sense to you, and it will. So you can do your sub-cases if you want, but this is really the vector expression of the force that a linear spring will exert on a particle of mass m given point of attachment Q. The bottom line is that every time you solve a problem with these, with springs, linear springs, you will better define this vector. You have to. You better compute the length of the spring, which is the difference between these two vectors, while k is given, and then figure out what this distance with this L minus L0 is. But that's all you need to use. Same way I gave you last time, the viscous friction is minus c times the vector VREL. That's all you need to use. Every time you have a problem, you figure out VREL. That's all you have to do. In this case, you have to figure out, well, L0 will be a given, of course. It's the unstretched, uncompressed length. You need to figure out L, the way to express L. We'll see a couple of problems. And a way to express US, and assemble this vector. Make sense? You have questions on this? Can you figure out what happens if you start thinking about Q fixed, it's not actually moving, and you are elongating the spring, and you make L minus L0 positive, US is pointing this way, well, then this minus takes care of it, and you have a pulling force, which makes sense. If you want to do that exercise, you can do it. But this is including every case: compression, extension. The 2 points may be moving in an inertial reference frame. Both of them, actually, I'm going to do that right away. There may be 2 masses at the end of the spring. How would you do that? With this definition I gave you, how would you address the case where Q also has a mass? So that's M1, this is M2. One spring.
2 different spring forces?
You define, yeah, in one case you treat Q as point of attachment, and you're looking at this particle, and then you look at this particle as the point of attachment, and the other particle is the one of interest. So that's what you will do. Still, the formula remains the same. You just have to define 2 US's in this case, which are opposite to each other, of course. There is really nothing special other than this is a simple expression, don't simplify it more than it is. It is a vector, and it needs to remain a vector. Okay, so that's really all I have. Oh, I have also a definition. I don't know if we really are going to see any problems with that, but let me give it to you. Where is it? I just want to be consistent here. The curvilinear spring. So if I give you a rigid curve, still in 3D Euclidean space, that's what it is. That's nothing new, really. But just for the sake of being complete here, let's talk about it for a minute. So say that you have now a rigid curve C, And then this is your point of attachment Q. Then you have a particle P that is moving on this curve and is attached to Q with what I'm calling a curvilinear spring. Okay. Then what I'm going to do is I'm going to use the, remember the tangent vector to the curve ET, and say that in this case, f of s is minus, it's the same formula, I don't think I'm going to use s, the arc length. So it's minus k s minus s0 ET in this case, where s is the length of the arc that goes from Q to P. It's the length of the spring in this case. It's not a straight line. It's a curve. But really, nothing changes. It's nothing special there. OK, so let's see this one first. I believe today we're going to see, maybe for the first and only time, I don't know, problems where I'm not going to use the transport theorem, probably. Unbelievable. But for once, we don't need it. So we have, okay, this is ground, which again is inertial. We have this guide here, and there is, so this is first point that I'm calling Q, attachment point for a linear spring, K, and then I have the actual particle mass m at the other end. So they are free, both of them, to slide on this guide along this horizontal line. No friction, there's only the spring. And say that Q, the position of Q of t is given. Remember that problem we solved with the angular momentum and without the angular momentum, where the attachment of the pendulum was moving horizontally with a given y of t? So this is given. That's a function of time that you know. What else do I need here? I'm telling you that the position of P with respect to Q is given by x, coordinate x, nothing else. I want the equation of motion. Now, today I have a terrible cold. I'm not very efficient. You guys do it. This is a very simple problem. It should be. Do you see any rotations? I don't see any rotations. Do I need more than a reference frame? That's the first question, right? Before you start writing anything, you just look at the problem and try to spell out in words, in plain English, or whatever your language, your primary language is, what it is that it's going on. So in my mind, I'm thinking, in Italian, that's my language, but I'm thinking that I see 2 points really moving. One has a mass, one doesn't. They move on the same line. I don't see the point of having more than one inertial reference frame, which is already there. So G, that's it. Okay. Tell me, coordinate system.
Coordinate Q when t equals 0.
That makes sense. So we say the origin is at Q when t equals 0. So we imagine we're freezing the position of Q wherever that is at a certain time 0. It could be also another time, but why not 0? Why not starting counting the time from where I freeze Q, and that's my origin. Then Q can move, of course. Okay, then what else?
Do we need to define anything more than EX for this problem?
You can count the X right there, so.
I'm sorry?
Just fine. So you put an X direction right there, so
Yeah,
kind of already.
to be completely honest, I probably won't need it, but going ahead of myself, what are the forces that are acting when we get to do the free body diagram that are acting on the particle mass m?
Gravity and spring force?
I can tell there is gravity.
Oh,
Just
that's
spring
one
force.
Just a spring force?
Oh, and friction and yeah.
Frictionless, okay. So what else?
Well, from the picture, it looks like.
Don't try to solve the problem. Don't think if at this point you shouldn't think, okay, that force may be there, but I think it's zero, so I don't think about it. No, just think about all the forces that could exist
No,
in principle.
what I'm thinking
Then
is
they
that
may be zero.
Q of T is acting on Q, not on P. So P shouldn't see Q of T. It should only see whatever the spring.
Yeah. Okay. Whatever Q is doing, when I do the free body diagram, I focus on that particle. I don't do anything else, and I will focus on the forces. So I agree that there's going to be some spring force on the particle P of mass m, and I don't know exactly which way it's going to point, and it's probably going to change with time, right? But there's also a reaction from the guide, right? That thing is constrained to move on the guide, and it may be that it's actually zero at all times, I don't know, but in principle, it does exist. So you're right, we'll probably solve the problem only on the x-axis, and I will not need anything else. But I think it's a good habit to define, even though this is simple, planar, not only planar, linear problem, I think it's better if you stick with the idea of defining all the vectors for each reference frame, all the vectors of the basis of the coordinate system for each reference frame, just because it's a good habit. If I had given you gravity, then you would have reaction and gravity. And then you would probably write the differential equation for that direction, and they may end up being equal and opposite at all times. Fine, but this is a very simple problem, but still. So I want to say EX along QP. That's fine. And just to be thorough, let's say that Z is out of page. And then EY is EZ cross with the X. This doesn't really waste too much of my time. It may be an overkill, but better to be safe than sorry, right? EX, EZ, AY. Okay. Fine. Actually, I don't need this for now. So the next step is, okay, I looked at the problem, I looked at the geometry of the problem, I defined my reference frames. In this case, I only need one. The coordinate systems associated with the reference frames. What is the next step? If I'm looking for a differential equation of motion, this in your mind needs to sound like F equal MAG, right? And so this translates into kinematics, kinetics. It's always the same story. You have to solve the two ends of this equation. So how do we get this? Of course, this is the acceleration of P, right? Bresh. Tell me. You tell me. Where do I start? This is an extremely simple problem, but that's the thing, even just defining x this way, or maybe if I had to define it in the other direction, could make your life a little harder. So, I'm sorry?
Get the velocity of P and then differentiate.
Well, so first I would say that you tell me the position of P. Now, this image looks like, in this case, that Q and X are counted from the same point. But remember that I picked an origin at some position of Q, which may have been this here, right? And that is from there that I'm actually measuring Q of T. So should make some fix to this image, right? Then x is actually from the current q to p. So it's always starting at q and going to p. And so, and again, this doesn't really mean to be going all the way there. Sorry. I just wanted to indicate that the position of q is given by a certain function. So it must be given with respect to the origin. So it's q plus x, right? Do we agree? Ex. And if this is, I can see that this may be confusing you a little bit, that after I first tell you q of t is given, and then I set the origin. But you know, someone may have given you q of t from this wall, maybe. And then I picked an origin that is not at this position at the wall, maybe somewhere else here. Well, subtract the two. It's not a big deal, right? So I'm not really giving you numbers here. It's all symbols. Will remain symbolic. OK, so if that's the position expressed in a basis which is attached to, fixed into the inertial reference frame, I can just take derivatives here, right? If p of g is q dot plus x dot ex, and then ap in g is q double dot plus x double dot ex, fine, I'm done with kinematics. OK, so this was kinematics. And then we go back to the free body diagram, and we say, OK, I have those two forces. This is my particle of mass m, spring force, which is, I know it's along the guide. I don't know anything else for now. And then some reaction, maybe, which is going to be on EY. OK, what is f of s? We start from the definition. You always start from the definition, and then you customize the definition to your particular problem. Start from the fundamentals. Don't skip steps. When I skip steps, I make mistakes, always. It's almost 100% guaranteed. OK, so I don't think I need this, right? You guys start figuring out the well, of course, L0, I'm also telling you that's given. Let's start figuring out the pieces here. What is u of s? Told you, you guys do it. You suggest.
It's x, right?
You prove it to me that it's c of x.
RP.
For what I told you before, it should be E of x, right? Because it goes from the point of attachment to the particle. But I want you to do it. You do it. Because this is a simple problem, and you can see it right away. In other problems, it may not be that simple. In other words, in this case, it happens to be along one of the bases, and it's really nice. In other cases, it may be that the geometry of the problem is such that you actually have to compute it, because it may be a combination of other vectors. So you can't just look at it and say, oh, that's u of s. Make sense? I may have springs in weird positions connected in different ways in 3 dimensions, and you need to compute them. So if it's Rp, what did I say? Rp minus Rq over the norm. OK. So that is, what is Rp? Minus over, well, the norm of all these, right? But what is this vector? If I subtract q of x, that's xex. That's what I get up there, right? Now, x in this case is always positive, because I defined it that way. I don't think the particle and Q are going to exchange position without going one inside the other. I mean, it's going to, it may be. No, it cannot be. I'm going to destroy the spring. It doesn't make any sense, right? So what I'm saying is that the norm of what I have, by the way, this is a vector, this is a vector, this is a vector. Yeah, the norm of this product, just to be thorough here, it's the norm absolute value of x times the norm of vector ex, which is the absolute value of x, which is x, because it's always positive. So it is ex, as you guessed at the beginning, because this is a simple problem, and you can figure it out pretty easily. But don't guess. Okay, that's US. What is L?
The denominator.
Yeah, I've done it.
Magnitude of RP minus RP.
It's the norm of this, right? It's this expression here. RP minus RQ, the norm. So it's X. That makes sense. I've defined X that way. It's obviously X. It's the distance between Q and P. And then L0 is given. Okay. We'll put it all together. So f of s is going to be equal, in this case, to minus k x minus L0 ex. And I believe your book has slightly different definition, so that this is an example on the book. I think the final result is minus kx ex without the L0, just because they define, I think they define the origin slightly different way. You can take a look, but doesn't make any difference. Okay, so I'm done here. I mean, my differential equation of motion is m q double dot plus x double dot ex equal to, oh, yes, minus k x minus L0 ex. Done. I mean, you can take the scalar parts and just equate those, and that's your differential equation of motion, right? Or if you want, I'm going to put it back here. This is one, and then the other one would be the following. M, what did I call? I didn't define a variable on the y direction, but let's say that I actually have done that. You would have m y double dot equal the normal force that I had in my free body diagram, but I know that this is 0 at all times, right? I know it's not going anywhere in that direction. So in this case, it's pointless to have EY and EZ probably, but I would not take any chances and drop things that doesn't take you too much long to define. So that's really your only differential equation of motion. It's always the same. Kinematics first, kinetics afterwards. Go with the models we have defined. Nothing new. Questions, concerns about this one? I'm going to do another one which is also simple. Oh, and I encourage you to do a case where, well, redo this by putting a mass in Q as well. It shouldn't be that painful, to be honest. Okay. See what I have here. This is in principle even simpler than the other one. It's the typical block here of mass m that is attached to a wall through a spring of constant k, and then calling this attachment point O. But this is the ground, which is inertial. But I am measuring x this way now. You're used to saying x pointing the other way, right? I was used to saying x coming from here, from the O, the origin O going towards the mass. I'm going to do the other way. And then you're more than welcome to do it with the classical x starting from O, counted from O. So what I have here is that the following hypothesis is that the unstretched length unstretched is L0, I give it to you, and then this is important, x is measured from the unstretched position. So what I'm saying is that if the block was here, that would be the unstretched length of the spring, right? I set my origin there, so I'm basically telling you that's the origin already. That's the point from which I'm measuring the position of the mass. What else? Nothing else? I want the differential equation of motion. I'm not going to write it down because it's always the same. Okay, exercise is the same. Reference frame, I only need one, but I better write it down. Is only the ground. The coordinate system now has an origin that I gave you. When the spring is unstretched, or when I say unstretched or I mean also uncompressed. So it's in its natural L0 length. It's not stretch, no compression. It's the same thing. So I gave it to you. I gave you that origin. And then EX, of course, is going to be. It makes sense, as before, to have it along MO. And if you want, you can define the other two. I don't see the problem. Out of page. Easy is out of page. And EY is easy cross with the X. And if this sounds like brainwashing you, well, it's better to be brainwashed on things that should be always there and you don't need to care about them. Because those are the ingredients that set up the problem for you, and if you mess them up, then you're going to end up with pages and pages of craziness that doesn't make any sense. So it's better to do this right. Okay. F equal ma is really what I want to write. And so the position of m, I'm going to drop mp, there's only one mass here. What is this? It's XEX, right? I mean, if you want to be a little more accurate with this drawing, I'm not that great when I draw stuff. This is the X, right? This is the 0x when it's unstretched, and then I count positions using that variable, XEX. So let's do a long story short. Acceleration of that mass in the inertial reference frame is x double dot EX. Fine. Free body diagram. Some spring force that I don't know which way is pointing for now. Some reaction force that I'm probably not going to care about. And this spring force is minus K L minus L0 US. U sub S. Someone gets me started on U sub S?
RM minus RO.
You can guess on this one too what you think it should be. If, again, I don't like you guessing, but for these simple problems you may see what you should expect as you've done it before. What do you think U sub S should be? And then we do it.
It's going to be EX.
Is it going to be EX? Exactly EX?
Well,
Look at EX. Remember the way I defined the unit vector of the direction of the spring is from which point to which point? Attachment to the mass. So I think it should be minus EX for the way I've defined EX, right? But let's prove it. So it should be R, well, there's no P, I don't know, R of the mass minus R of that point O, which is the attachment, minus over the norm of this same vector, right? Make sense? So the first one is what I just wrote there. It's X, EX. What is R0? RO. The position of that point O. What is that? I define the reference frame and I define a coordinate system. I want to use that coordinate system. Is it X? It's L0. L0 EX. Because I define my origin to be at the position of the mass where the spring is unstretched, and that length I called it L0. So if I am measuring things from this point, and that's the positive direction, this O is L0 EX. See, I just changed the way the origin is defined, the direction X is defined, and the problem may not seem that obvious. So, okay. Then what do I have here? Same, right? I have to do the norm of that. Now I have X minus L0 EX over same thing that we've done before. I have the norm of this same vector down here, which would be the absolute value of X minus L0 times the norm of EX, which is a 1. Okay, what is this? What is the sign of X minus L0? It's always negative, right? For the way I define the X. It's a weird way of defining X, but it makes me think. X is counted from here. So this is L0, right? Say 3 meters. Position of the mass is not going to be ever more than 3 meters counted from that point. Otherwise, it will just go inside the wall and destroy everything, but that's not going to happen. So X minus L0, if I think about the mass going this way, it's definitely negative. X is less than L0 in magnitude. If it goes that way, X becomes negative. So this definitely is going to be negative. No matter what, it's negative. So if I remove the absolute value, I get X minus L0 times EX over L0 minus X. Make sense? These are minutiae. These are small things that are not that small. They make a huge difference, because then if you don't do it that way, and you've defined the origin as I have, you get the wrong sign. So minus EX, which is consistent with the observation, oh, okay, yeah, it's from the attachment point to the mass. Makes sense. Good. And I'm almost done. I equate MA, so MX double dot EX to, well, I'm going ahead of myself. That was only US, right? Okay, L0 is given. What is L? Sorry. What is L? Length of the spring. I defined it to be the magnitude of that vector, right? So I don't need to redo it. But the magnitude of that vector was L0 minus x. Right, okay. And so my f of s, in the end, now I can put it all together. The force of the spring is minus this k, someone gave me the k. L is L0 minus x minus L0 time us, which is minus big Ex, which is, to go away, minus, minus, minus. Make sense? Now you want to go through your exercise. If you compress, the x is that way, x is going this way, you get a force, negative Ex. If you pull the other way, x becomes negative. You go the other way, but you don't really see this thinking, this exercise can maybe come after you have gone through the definition and you found your final expression for the force. Then you can start imagining all these cases if you want, which for a simple case like this is possible. For more complicated cases, it may not be that easy. When you have two masses involved, it becomes more difficult. But you don't do that before you define you find what the force of the spring is. You find what the force of the spring is by the definition, going by the definition, then you can do your exercise if you want. And I'm telling you that because for years I've done it myself. I do that exercise to figure out what is the expression for the force of spring. I do all the subcases. And when there are two masses, there are more subcases. And when there are three masses and two springs, it becomes a mess. And it doesn't need to become a mess. Because there is a clear definition. Then once you found it, you can test your hypothesis and do whatever you want mentally. But you apply the definition first. OK, I think we're done. That's f of s. That's your differential equation of motion if you want. I mean, that's nothing new, right? We've seen this before. But what we've seen before is that this is where people would start from, telling that the force of spring is minus kx. Well, yeah, after you have projected, it may be minus akx. But that's for a problem like this. Problems can get more complicated than this. Any questions, concerns about this? Any questions, concerns about everything that we've seen so far? Test is in about 2 weeks, right? So you are working on chapter 2 and 3 at this point. Told you not all the problems have solutions. If you have issues with those without solutions, or even with those with solutions, of course, you really should come see me. I don't see too many people coming to office hours. So I hope that's a good sign. Okay, thanks.